Today we're going to go over quadratic attributes and the transformations. So we're going to start with some vocab here for the quadratic unit. We'll start with vertex. And the vertex is where it changes direction in our parabola here. So if we've got a vertex like this, or a parabola like this, the vertex is at the very top. It is the point where it is increasing here and then it starts to decrease. So this is our vertex, that point where it changes the direction. In this case, that vertex would be a max. If our parabola opened upward like this, then we would have a min vertex here because it's the smallest point on the graph. Again, it's that point where it's changing direction, or that max or min point. Now the roots or zeros, and you'll hear them be called solutions or x-intercepts as well. Those are the points where it crosses the x-axis. So this point right here and this one. Those are your solutions or your x-intercepts or your roots. They are interchangeable, so you'll hear them called all of those. If the vertex was on the x-axis, it too would be a root, so it'd be a vertex and a root. And if it doesn't touch the x-axis like this, it would be two imaginary ones. So these are our real solutions right here, and then we've got imaginary ones we'll get to later on. The y-intercept is where it crosses the y-axis. It's that ordered pair right there where it crosses the y-axis. We'll see later that that is the c value on the standard form, so that is 0, c. All right, for our maximum, we talked about that. On a quadratic that opens downward, our max point is this right here. A quadratic that opens upward only has a minimum point right there. So this would be a max quadratic, this would be a min one. Our concavity is which direction it opens. And so it is up if our quadratic opens up, or down if it opens down. The axis of symmetry, which we will refer to as the AOS most of the time, is the line that cuts our parabola in half. Since we're working with parabolas that open up and down right now, it is always going to be a vertical line. Vertical lines are always x equals. So you'll write the equation as x equals whatever that number is. And that number is going to be whatever the vertex is, since that line has to go through the vertex. That's where we would fold that parabola in half, and all of these points on the left-hand side would land right on top of the ones on the right-hand side. So there is symmetry on both sides. Every point that happens to the left happens to the right. So it goes through the vertex. All right, so there's all our parts to the quadratic, or what we call a parabola here. So now we're going to look at an example of where you would get that information. So here is a parabola. It's talking about seconds and feet, so this would be a real life situation parabola. We're going to talk about the different parts from it. So the vertex is this point right here where it changes direction. So it is at 4, 9. It is an ordered pair, so you should be answering as an ordered pair. It's asking you if this is a max or a min. That is a max vertex since it opens downward. And so our concavity would be down. For our domain, the first x value here would be 0 and the last one would be 8 since it's talking about seconds. So our x values all go from 0 to 8. And so we write 0, 8. Remember, with domain and range, that's the smallest number, biggest number. There is a point at 0 and there is a point at 8, so we will have brackets for that. If you wrote it as an inequality, it would look like that. For our range, the smallest y value here is 0. Then we have all of these y values until we get to 9. That's the biggest y value, so our range would be 0, 9. There is a point at 0 and a point at 9, so we've got brackets. And if you wrote that as an inequality, it would look like that. Our roots are the points that it crosses the x-axis, so we've got two of those, one right there at 0, 0, and one at 8, 0. Our axis of symmetry, that's our AOS. We said that's the vertical line that cuts this in half, where we see everything on the other side of the line is exactly the same. So this would be our axis of symmetry right there. Again, it goes through the vertex. So it's going to be x equals whatever that x value is of the vertex. So that's going to be 4 in this case. It is a line, so you have to write it as the equation of a line. All right, so let's talk about the parent function here. The quadratic parent function is y equals x squared, and we said that graph's a parabola. If you think about the table of values for a quadratic, 0 squared is 0, 1 squared is 1, 2 squared is 4. So that's going to give me 0, 0, 1, 1, 2, 4, and you can even go further, 3, 9, if you wanted to go further on that graph. We said it is symmetrical, so whatever's happening to the right is also going to happen to the left. So we would get negative 1, 1, negative 2, 4, and negative 3, 9. And so we connect our points here and we get this parabola, U-shaped graph. The domain of all quadratics is all real numbers. It goes from negative infinity to positive infinity because as it moves, it's going to move all the way to the left and it's going to move all the way to the right as it goes up as well. Our range is going to start right here at the vertex and go up if it is a concave up parabola. If it was a concave down parabola, it would come from negative infinity up to the vertex and then back down. So those are the two different types of range we're going to see. It's going to start at 0, we said, and then go up to infinity. This value is always going to be that vertex y value, because our vertex here is 0, 0. The axis of symmetry, that always cuts right through the vertex. Our axis of symmetry here happens to be the y-axis. It is cutting through this point right here, so it is x equals 0, which is the x value of the vertex. This graph is both increasing and decreasing at different parts. And so when we talked about increasing and decreasing earlier, it is decreasing right here until it hits this point, then starts to increase as it goes to the right. So we're trying to show people where is it increasing and decreasing. We want to say this left-hand side is decreasing, this right-hand side is increasing. We don't want to give them the y values because they repeat, so that's not going to give them a good picture. It's the x values we want to tell them since those do not repeat. So left-hand side is decreasing, right-hand side is increasing. So we say from negative infinity to 0. And that's the one that we told you can't have a bracket or a parentheses on it. Oops, sorry, wrote that on the increasing, that's the decreasing. All right, on the increasing, it starts right here at 0 and goes up. So we want to say this right-hand side, so 0 is the smallest x value there, and infinity would be the biggest, so that goes from 0 to infinity. Sorry about that mess up there. All right, so let's talk about transformations now with quadratics. We always start with this parent function because this is going to be our starting point for everything. We start with this and then we do the transformations to that. So our transformational form of the equation looks like this. We've discussed the A, the B, the C, and the D before, and they do exactly the same thing they did in absolute values. They're going to do exactly the same thing on all of our functions here. A is the vertical stretching and compressing, and it reflects across the x. B, which is inside of the operation, so it is it's on the inside of that square. That's your horizontal stretching and compressing, and it reflects across the y. This goes right or left on the C, and then the D goes up and down. Been seeing lots of errors with this. Remember, x minus c goes to the right, x plus c goes to the left. And we'll explain that further right here when we take this example. So our parent function's our starting point, and here is our transforms equation. Outside of the function, so our a value, we have a 2. We do not have a b value here since there's nothing in front of it, so that's just a 1. It's not going to change our equation at all. The c value here, it is supposed to be x minus c in the formula. So this says x minus 4, so our c value is a positive 4 because the minus is part of the formula. The d is 1. So we're going to think about what that does to each point. For our little formula here for our points, it shows you the horizontal stretching or compressing is going to change our x values, since when we horizontally stretch or compress, we are going this way. So that's going to change our x value, so we multiply times that scale factor, 1 over b times x. The c value moves it left to right, so it too is going to change the x, because it's on the inside of this operation, so it's changing our x values. The ones that are on the outside, that's going to change our y values. Vertical stretch or compressing goes this way, so that's going to change my y's and not my x's. Same thing with the up and down, so that is going to change my y as well. So we didn't have a b here, 1 over 1 is just 1, so I didn't put anything multiplied times my x values, and we just started with the key points from the parent function. Our c value though is 4, so we're going to add 4 to each one of those x values. And so 0 plus 4 gives me 4, 1 plus 4 gives me 5, and 2 plus 4 gives me 6. So those would be our new x values. For our y values, we need to multiply times the scale factor. So we're going to multiply each one of these y values times 2. And then we're going to add 1 because that's our d value. So 2 times 0 is 0 plus 1 is 1. 2 times 1 is 2 plus 1 is 3. And 2 times 4 is 8 plus 1 is 9. So now we've got our new points, and I'm going to go ahead and graph them here so we can see the difference. So 0, 0, 1, 1, and 2, 4 is what we had graphed for the parent function, and we said it is symmetrical across that vertex. So here is our parent function. This is f of x equals x squared. All right, here we're going to do our g of x is equal to 2 times f of x minus 4 plus 1. In this case, we've got these new points. So 4, 1, 5, 3, and 6, 9. And whatever happens on the right must also happen on the left, since we know it is symmetrical across the vertex. So we've got this parabola here. And so as we're looking at these two parabolas, we see that from our parent function to this new vertex, we have moved to the right 4 and up 1. That's what that c and d did. We can also see that this one on the right is skinnier. Our g of x is skinnier than our f of x equals x squared. That's because we took this parent function and we stretched it here. That's what that a value does. That's that vertical stretch. So we vertical stretch by 2. We moved it to the right 4 and up 1. It's really important that you know what each one of these does, the transformations, because it helps us graph that way. So if we know these transformations, it is easy to take our parent function and graph it without a calculator, just like we just did. So we're going to practice some more of those on this side here. We've got y is equal to -1/2 x plus 3 squared plus 5. So we've got a couple transformations there, and you want to take each transformation into account when you look at these to graph them. So our first transformation is a reflection across the x. That's that negative out in the front. We said when the negative is outside of the operation, that's a reflection across the x. This 1/2, that's the a value again because it's outside of the operation. That would be a vertical compression by 1/2. And then the x plus 3, that is left 3. And then the plus 5 is up 5. So when you're graphing this without a calculator, you can use your parent function in these transformations to graph it. I start with my parent function of 0, 0. Now when I multiply this times 0, it's not going to change anything, but I can move it to the left and up 5. So left 3, up 5, here is the new vertex. The vertex is always going to represent those two numbers, so keep that in mind. Now our next points, the next point over should go over 1 and up 1. But because we have a reflection across the x, we know it's going to go downward instead of upward. And then instead of going a full unit, it's going to go 1/2 because 1 times 1/2 is 1/2. So we would go to the right one and down 1/2. There's that vertical compression. The next value is supposed to go to the right 2 and up 4. Again, it flipped over the x-axis, so we would have it going downwards instead. And then we have to shrink it by 1/2 because of that vertical compression. So that's one way of looking at it right there to graph. The other way is you can actually do it from the initial point. So we can start at this one right here, which would have been the second point. We flip it over the x-axis, we shrink it by 1/2, then we move it to the left 3 and move it up 5. And there it is right there where we were. So you can either start with the 1, 1 and do it that way, or you can think about the points according to the vertex. With this second example, this is one that students miss a lot, and that's because it is not in the transformational form the way it is here. So students want to say this went to the left 6. It did not. It's not in the transformational form. Before we can start picking transformations, we've got to go ahead and set it up in the transformational form. To do that, we factor out that 2 in the front there so that x doesn't have anything in front of it. So 2 times x gives me 2x, and 2 times 3 gives me this 6. We factored out whatever's in front of the x, so that GCF, we factored it out. Remember, factoring is undoing that distribution. Now it is in the correct transformational form, so now we can take our transformations from it. Over here we've got a down 4, left 3, and then this 2 on the inside. That's our b value. And so we said if it's bigger than 1, it is a horizontal compression. And the scale factor is flipped, so that's by 1/2. This is what we would multiply our x values times, 1/2. So 0, 0, again, goes to the left 3 and down 4. So there's our vertex. Notice again, we're using those points. That's going to be our vertex. That'll be useful later. And then our horizontal compression. The next point is supposed to go over 1 and up 1. But we are compressing it by 1/2, so it is going to go over 1/2 and up 1. We're taking it in from the sides there, so we're horizontally compressing this way. The next point is supposed to go to the right 2 and up 4, but we're compressing that by 1/2, so it is only going to go to the right 1 and up 4. Did not change those y values, it only changed the x values. And then we would connect those points. I'm going to quickly do the domain and range with these just so that you can think about that. We said the domain is all real numbers for quadratics because it goes all the way to the left and all the way to the right. For our range on this one, it is coming from -infinity up to this point right here, which is at 5. So we would say -infinity to 5. For this one, our domain again is all real numbers. That's true for all quadratics. And then our range is going to be from -4, which is my vertex, to infinity. In both cases, we use the value from the vertex. So keep in mind that 5 right there, which is our vertex, is the value on the range. Same thing here, our -4, which is the y value of the vertex, is part of our range here. All right, the last example we're going to do is from tables. So looking at our, actually, sorry, let me talk about the increasing and decreasing real quick on these. For our increasing and decreasing, we can see this part is increasing until it hits my vertex and then it starts to decrease. It changes that direction there. So we want to say this left-hand side is increasing and the right-hand side is decreasing. So to point this out for other people, just kind of drawing them a picture, that's what the increasing and decreasing does. We want to make sure that we tell them the x values because the y values repeat, and that doesn't help them think about where it's increasing and decreasing. So up to -3, notice that's the vertex piece. So from -infinity to -3, it is increasing. So -infinity to -3. It is decreasing from -3 to infinity. That's that right-hand side of the graph. Over here, we are decreasing on this left-hand side. So from -infinity up to -3, and then we are increasing from -3 to infinity. All right, now our last example, we're going to do transformations from a table here. And the most important part here is that you're able to find that vertex. That's the place that's going to help you write the equation and think about the transformations. So we're looking for that symmetry. We see here it went from 0 to -1 to 0. So this has to be my vertex. It's the point that doesn't have the symmetry, that we see the symmetry around. It's also going down and then back up, so we can also see that change in direction there. For this table, our vertex is then -3, -2. We see that it is going down, hits this point, and starts to go back up. We also see the symmetry around it. So we want to think about what happens from 0, -1 to -3, -2. I'll go ahead and sketch a quick graph so you can see that. Here is our g of x point, here is our f of x point. So we're starting with this f of x, so it went to the left 1, 2, 3, and down 1. So we've got a left 3 and down 1. Now we want to go ahead and make sure there's not a stretch or compression or a reflection. Both of these points are 1 unit above the vertex. On this one, again, both of these points are 1 unit above the vertex. So we know that there is not a reflection and there's not a stretch or compression. So these are only 2 transformations. So we would say g of x is equal to our f function, left 3 and down 1. We do not put a square here. Once you put that square there, you are only comparing it to the parent function. And these are the transformations from this function to this one. It is not from the parent function. So the minute we put a square there, we're talking about the parent function, not a transform function. So we write it in this functional notation, which says f. This f right here tells you use this one and move it to the left 3 and down 1.